Right. So this week we have the pleasure of having our friend Alice speak. She's going to talk to us about COVID-19 spreading and Eigenvalue Viewpoint. So Alice, it's all yours.
Hello, I'm Alice, and my topic today is COVID-19 spreading and Eigenvalue Viewpoint. I think in this department, nobody else could be more suitable to talk about this because of nationality. So here's the brief view of today's talk. First, I'm going to introduce the current status of the COVID-19 spreading and some classical models about the viral propagations. The next is the main part of why we want to model a new nonlinear dynamic system, and some results come from it is the epidemic threshold, and we gonna prove it and get some conclusions to really apply to the real case of the virus spreading. We call it immunization, and then we're gonna draw some conclusions and maybe future work or Q&A. Okay, so that's briefly what we're gonna do today. Coronavirus, actually COVID. I took a screenshot from the Johns Hopkins Universities, which demonstrates, I think I took this screenshot like 2 days ago, and you could see that the total cases and total deaths almost reached 5 million people. And those red dots denotes that the which area is gonna be the most affected in the worldwide case. Actually, coronavirus COVID, we call it COVs. It have so many branches like alpha, beta, which infected mammals, I think. And in 2002, there was an outbreak called SARS in China, and it belongs to the beta COVID. So I think the death rate is around like 11%. And while there was other two, it's called Delta and Gamma branches of coronavirus, it's only infected birds. So regarding to the COVID-19, it happened earlier in December 2019 in China, so that's why we call it COVID-19. It also belongs to the beta branch of the COVID, so we also call it SARS-CoV-2. And nowadays, as you see the photos here, the graphs, it's spread so quick to over 100 countries in the world. But however, there's still no matured vaccine. And my definition of mature is it's not still not acceptable for the young kids or some other type of individuals against the SARS. I mean, and some specific drugs for treatment of the communicative diseases. So it's very essential to get a better understanding of the COVID-19 for exploring some effective and healthy vaccine and drugs for it. Okay. We're not talking about a vaccinated. We're interested in the mathematical modeling of it. Actually, the origin of such modeling was developed in earlier 20th centuries. Okay. There was the population is assigned to compartments with labeled S. Here means susceptible, I means that infective, and R means that removed. Removed here means that you either dead or you healthy again. So we call it removed.
So hold on, dead and recovered go in the same box?
Yeah.
Okay.
We got removed. Yeah, you just removed from the population that you are interested in. So
I guess, so recovered means that they can't get sick again, or I don't know. Looked into the model.
Recovered. No, R removed here means that we considering the populations with two group of people. You either dead from it or you healthy.
So dead means they can't get it again. Healthy means, I guess, in this model.
Very good question. So this is I'm gonna talking about the SIR model. Okay. So the people may progress between the compartments, and the order of the labels usually show the flu patterns between the compartments. So for example, like SRR, IR means that the individual is gonna be susceptible and then get infected and removed. So the similar case for SIS. So it means that it's from susceptible to infectious actually, and go back to susceptible again. So let's see what is SIR means. Like, this is very simplest models and reasonably predictive for some infectious diseases. And these infectious diseases have a very unique characters. It have a recovery lasting resistance, such like mumps. Okay, so if you got immunity, you're gonna never have it anymore. Okay, so I show you some graph here, and you could see the yellow. Actually, we could the variables here, SIR, represent the numbers of the people in each state with respect to the time t. As actually, the model is dynamic. Okay, the yellow dot line here means that the populations were susceptible, and then the active, and the toes one shows that people were removed, I mean healthy or dead. Okay, so you can see that at the very beginning everybody was healthy, and as time goes on, more and more people get infected. And well, since we're doing some immunities, we get a long-lasting resistance from the diseases, everyone going back to healthy or dead again. Okay, back to the same level. Well, in our case, some infections such as common flu or COVID-19 that do not confer any long-lasting immunity. So such infectious diseases like COVID-19 did not give you immunity upon recovery from infections, which means that you get a COVID and maybe in 3 months later you get again. Okay, or even vaccinated, but you still get it again, maybe in 1 or 2 days. So individuals become suspected again, even though you were, anyway, you do not have a long-lasting resistance from the diseases. So as shown in this graph, you can see that this is a very special case. Each of them reached to equilibrium point, but more and more research, they were focused on the epidemic threshold, which could be evaluated to how to control the propagations. Why? Because in this case, because literally think that everybody gonna be infectious, gonna be infected by the diseases, because you really don't have any movement or treatment to deal with that. Okay, so what we're really curious about is the epidemic threshold, in which case we could control the propagations, and we do not want the situation getting worse. Okay. And those classical mathematical models, they have some shortage. Okay, they have assumptions or limitations of their topology of the network or the physical, connections. So here comes a question: does there exist a generalized model and with no requirements of the graph topology? The answer is yes. Okay, so we're gonna derive models that was no assumptions of the topology. So here it is. So let's get started with the some notations. Okay, so we assume we have a connected undirected network, which denoted as capital G, and NE. N here means that the nodes, the total number of the nodes in this network, and E is the edges. Okay, and beta we define as the universal infection rate, and correspondingly we define the delta is the killing rate, or we can say that the virus death rate. Okay. And also we have a probabilities of each node. We can consider like individual I is infected at a time t. We denote as a PIT. Okay, so PIT means that the node I at time t got infected, the probability of that. Okay. So our models actually works with very small discretized time step delta t, but the same result could also hold for the continuous case. Okay. So during each time step, time interval like a delta t, each node I or each individual I tries to infect his neighbor, okay, with a probability beta here. And at the same time, I may get cured with the probability delta. Okay. Okay. And so now we define another probability. Node I will not receive infection from his neighbors at time t. Okay. We define as eta it. So the eta it actually have two parts. Okay. The first part is either the neighbors is not infected. So 1 minus pjt 1 minus 1 knows that the neighbors is not infected, or the neighbors is infected but it fails to infect the node I. So pjt minus 1 times 1 minus beta.
So
Okay.
quick clarification, I guess.
Sure.
T is discrete. It's discrete time steps.
Yeah.
Okay. Okay.
Mm-hmm. And we did okay. Any other question? We did a little simplifications, and we got this. The product of the 1 minus beta pj t minus 1. Actually, this is a Markov Chen. Could be modeled like Markov Chen with 2 to the nth states. So you have 2 states, you have n nodes. So there was totally 2 to the n states. Well, it's kind of like hard to compute it. Okay, so we actually consider a very, very small time step. Like the probability of multiple events with the same delta t is small enough, you can ignore it compared with the first order effects. So that's why we have a simplified version, and this version actually being solvable. And we also have independent assumptions that we assume that the time step t minus 1 are independent with each other. Okay, so so we derive a node I, which is not infected, which means that is being healthy from its neighbors. We denote as eta it. Okay. Next, I'm gonna show you actually I want to illustrate the flow. So the figure shows that the ISI models as seen from one single node. So for one person or individuals is either suspectable or infective. So it's gonna be from a suspectable state to infected by its neighbor. The probability is 1 minus eta it, and it's being cured by the delta. Okay, so next we're gonna define the house probability of the node I in individual I at the time t, which is 1 minus the infectious probability. Actually, it still consists of like 2 parts. Okay, the first part is like the node at time step t minus 1 is healthy and it's not being infected by its neighbor. So the first term gonna be 1 minus p times eta it. Okay, or it is infected, but it's cured at the next step. So it minus 1 times the delta. Okay, so it consists of like these 2 parts. Actually, this equation 2 here represents a nonlinear dynamic system, and we're gonna have some results from this dynamic system to reach to our epidemic threshold.
So another question, I guess. So this is all this thing happens at a single node, yeah? So they're susceptible and infective at.
Yeah, it's a single node.
Okay,
yeah.
Okay, I see. And then, okay. I think I understand. Cool.
Okay, More questions? So this is actually, I'd give you discretize the time, discretize the scheme, and you can solve it numerically, right? All right. Okay, let me see. So we have a questions like, under which conditions we can control the pandemic? Okay, so there's a definition, it's called epidemic threshold. Actually, it's a value tau. So the value tau here is if the infectious rates over the killing rate is less than tau, means that the pandemic gonna dies out. Okay, well, if the infectious rate over the killing rate is bigger than tau, and it's become an epidemic, and you can't do anything with it. Okay, so it's just a little bit of brief definitions of it. So, so here's our theorem. Is in our models, epidemic threshold tau. Actually, we have a very brief definitions of that, equations of that, which is the inverse of the largest eigenvalue of the adjacency matrix A of the network. So what is the adjacency matrix? Here I give you, I show you a labeled graph. One, there was a 6 nodes in this connected network. And you could see that I labeled it as 1, 2, 3, 4, 5, 6. And each of them can have some connections between each other, but no directions. So you could also see that some label graph, they have a direction, but we do not consider directions in our case. Well, we also do not consider about self-infectious because you can't just let yourself get infected again by yourself, you understand? So we do not consider, but you may see some articles, they said they were considering something of the self loop or whatever, but so we do not consider in our case. Okay.
Alice, I have a question.
Okay.
How did you define this adjacency matrix? What's the ijth value? It counts the number of what paths from the vertices ij. Is that how you would define it?
Which one?
There's 1 if there's nearest neighbor between vertex I and j, and 0 otherwise. And in the case there was a 2 on the diagonal, that was because there's loop.
Oh, okay. 2 is loop. Okay.
Yeah, 2 is a loop. So you could see that if we do not consider the self loop, so this entry is going to be 0 as the other nodes. So the diagonal of the matrix is always 0. And if you have a connect with the corresponding like nodes, you have the 1 entries at the corresponding positions in the matrix. Okay, so okay. The matrix is diagonalized. I mean 0 diagonalized and is symmetric. Okay. So for example, if you are considering the second row, which denotes that the connections of the second node, so the second node have a bound with the first node, so we put 1 here, and also have a connection with 3, so we have an entry 1 for the 3rd position, and same thing for the 5th. So if you did the same thing, you can see this is a symmetric. I mean, if you did not consider self loop, like always 0, and it's real symmetric matrix. Okay. All right, so this is our theorem. We say that the tau, the threshold tau, is defined like the inverse of the eigenvalues. Okay. And we're gonna show that why it is. So the idea of the proof is that we're gonna translate the problem, the virus virus problems into the stability of the nonlinear system. Okay, so if a system is stable, a system is stable if the first eigenvalue is very small and unstable otherwise. And so a stable nonlinear dynamic system also implies that if you have a small perturbations, and will eventually returns to all nodes healthy state. Okay. All right, so we're gonna prove in two directions, necessities and sufficiencies. Okay, so let's take a look at part A. So we're gonna prove it direct in two directions, necessities and sufficiencies. Okay. So if we want epidemic, dies out, we must have the tau equals to 1 over number 1A. That's what we're gonna show. Okay. So we have this scheme we derived earlier, and actually the left-hand side is at time step t, and the right-hand side is at time step t minus 1. So it gave us a inspiration. We can write into the equivalent vector form like a pt equals to some function g pt minus 1. Okay, and the function g for a node I gonna be derived like this. We just move the constant to the right hand side. Okay, and here, so we want the the epidemic dies out, means that we want the probabilities goes to 0. Okay, we want the left-hand side goes to 0. So if it's very easy to check that if the vector p is equal to 0, then I mean, it's easy to check that p equals to 0 is a fixed point of this system. It's very easy to check it. And if the pt at the time level t minus 1 equals to 0, given you this, and then you're gonna have the probability at time t equals to 0 too. But here is another question we still need to answer is, so if the infection probability of all nodes come close to 0, will the dynamic system push even closer to 0? So in other words, like the question I posted here, is the p equals to 0 fixed point asymptotically stable? If the answer is yes, the infection probability will go to 0 and the infection is going to die out. And if not, then okay. So it seems like we need something else to answer the questions. We're going to use the dynamic system theories. Here's a lemma. So the system is asymptotically stable at p equals to 0 if the absolute values of the eigenvalues of this gradient G0 is less or equal to 1. Okay. And you could see the brief proof of this lemma in a book. I think it's called Differential Equation, Dynamic System and Algebra by Hirsch and Smell in 1974. I think it's a 2-page proof. And we're gonna use this lemma. So what are we gonna do is we have to calculate the eigenvalues and absolute value of the gradient G and make it less than 1 to make the system stable. So we're gonna prove it. We calculated the gradient of this. Actually, we know that if I equals to j, the diagonal entry is always 0. And if I is not equals to j, and you may have something adjacency matrix times the beta. And we combine the two into this form. And that equation holds because the adjacency matrix is symmetric. Okay, so A prime is equal to A. All right. And you could see that this is actually a matrix that could describe the behavior of the infection. So we name it as system matrix S, and we denote it as S and equals to the right-hand side of beta A plus 1 minus delta times identity matrix. Okay, and next we're gonna find, remember, we have to find the eigenvalues of the system matrix S, and we want to make it less than 1. Okay, and here we have another lemma. I'm gonna prove the lemma later on. The lemma is the i's eigenvalues of S is in this form, and the eigenvectors of S are the same as the matrix A. Okay, so we so proof continued. we have the eigenvalues in this.
Lambda IS is 1 minus delta plus beta lambda, probably IA, yeah?
Oh yeah.
Okay, just
give me
checking. I mean, that would,
one
otherwise they're all the same eigenvalue, which would make less sense. But yeah, okay. You write it below, so I think that has to be it.
Yeah, I think it's gonna be IA. Thank you. Yeah. Let me double check. Yeah, IA. Yeah, good catch. Okay, so we're gonna use that. And the system is simple, asymptotically stable when the absolute values of that is less than 1 for all I. Okay, and remember that the matrix A, okay, A here is a real symmetric, and the same things for the S, because this is how we define S. Okay, so we have these conclusions that the largest eigenvalues is positive. And the largest eigenvalues of the S is real positive and also has the largest magnitude among all the eigenvalues by Person-Frobenius theorem. Okay, so we denote the largest one as lambda 1s, and it is real positive, so that's equals to the absolute values, and it's always the largest one among all the eigenvalues. So we have this equation holds. So we plug back in the assumptions, and we eventually implies the tau actually equals to 1 minus our eigenvalues. Okay, so that's the necessities of the epidemic threshold. I want to prove this lemma real quick. So why is the eigenvalues of S have this form? Okay, it's pretty easy. We just denote the eigenvectors of the A as UIA with corresponding eigenvalues, and then we have this scheme. So we kind of like operate with the UIA both sides. And from the first equation to the second, we use the definitions of the eigenvalues, and then we simply just connect some terms, and we got the last equations. So from the left-hand side to the right-hand side, you can see that the UIA actually is a eigenvectors of the S with the corresponding eigenvalues 1 minus delta plus beta lambda 1a, which is exactly the lemma said. And I skipped the other directions because we did not use this direction, but it's very easy to prove. Okay. So the necessity was down. Any questions?
So far, so good.
Good. Okay, let's prove the sufficiencies. So if we have the tau equals to the inverse, and then the epidemic will dies out. Okay. So we're gonna do some trick with the eta IT. Remember, eta IT is the probability that the node gets infected from its neighbor. So this is the definitions. Okay. And ever since the terms in this right-hand side are always positive, so we have this inequality holds, but it needs a little bit of gyrations. Okay. But it's only, but what I really use is all the terms of positives. You have this equation holds, but it needs a little bit of calculations. And ever since our scheme is this, okay. So we just plug in those inequalities back to the nonlinear system, discretize the form, and we're gonna get the PIT is less or equal to the right-hand side is always about the t minus 1 scheme. And here I just use the adjacency matrix to replace the neighborhood, summation of the neighborhood here. Okay. And it gives us some ideas like this, kind of like the system matrix we defined earlier, S. So remember, S is equal to 1 minus delta times identity matrix plus beta times something. And then we could rewrite into vector form again and do the iterations. So SPT minus 1, that's equal to S squared, and blah, 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 and then ends up with S to the T times P0 vectors. And the last equation is because we expand, we use the spiritual decompositions with the S to the T, okay? And we haven't used the assumption yet, okay? So what is our assumption? We assumption like we have the tau is equal to the inverse of the eigenvalues. So we just plug in and we have that this eigenvalues here is less than or equal than 1. So what does that mean? It means that given you a very a less than 1 here, as if you were considering a large enough time t, and p gonna goes to 0 as it's showing here. So the p goes to 0 also means that the infections probability goes to 0 and the pandemic dies out. Okay. So that's the proof of the sufficiency. Any questions? No. No. Okay. Oh.
I was just saying not about the proof, but I might have a question in a second. But let's see.
Okay. So we have another questions come out is if we were under those epidemic threshold, so how long are we gonna expect the things gonna die out? Okay, so I take a screenshot of the worldwide cases, and you can see that some drop here. Okay, maybe another variant like alpha, beta, gamma, something. But why is the drop like this? Well, it could be seen from our calculation. So P actually is less or equal to the right-hand side. And the last 3 terms actually is the constant vectors. We can denote as C. I forget to put an arrow here. So it's easy to see that the values of the probabilities are decreasing exponentially, over the time t. So we could expect exponential decay, okay, because of this. Okay. Right. So as regarding to the applications of our, models, we have a something called immunization. So the question is gonna be, if you have a budget of K knots that can be immunized, which knots should we pick? Okay, any idea? Well, the targeted, the previous or the old immunization policies will choose the knots have the highest degrees. Well, based on the theorem, we just proved that we should choose the one that caused the maximal reductions in the lambda 1A. Why? It's because that if you are under control, which means that if those things is less than 1 and this actually equals to the tau, which is 1 over lambda 1A, we just move to the left hand side. We want this one as small as enough.
So maybe it's graph specific, but is that, I think it goes along with what you're saying, or maybe you'll say it again in a second. So the intuitive answer, I think, is that you pick the ones with the highest degree, like you just said. You pick nodes with the highest degree because the ones with the highest degree are the ones that are most connected, and so that will, at least naively, reduce the spread the fastest. But this says something else, like slightly different. Yeah, maximal reduction, and the one that actually does it is the one that maximally reduces lambda 1. Yeah.
I'll give you an example real quick.
Okay. Yeah, I'm wondering if the two are the same, or if you can actually, like, if one implies the other, or maybe it's not even correlated.
Yeah, maybe no. I'm gonna show you examples here. So we have this barbell graph, okay, and the graph consisting 2 equal size clip, okay, connect with a bridge here, C, okay, and so we're gonna assume that K here gonna be 1. So you have a budget that you could only immunize 1 knot. Which one you should pick? So you can consider like the degree of the A, for example, 2, 3, 4, 5, 6, 6, and similar things for A prime. B might be more, like 1, 2, 3, 4, 5, 6, 7, right? C only have 2 degrees, right? So guess which one you want to pick to immunize. I mean, to get rid of this graph.
So it'd have to be, I mean, if probably C would be good, yeah? Because if one is infected and you delete C, then okay, so that it is different. That's interesting. Okay.
Yeah, that is different, right? So as I said that, okay, so intuitively we know that it's gonna be C, but why? We're gonna calculate the lambda 1A. So without immunizations, the lambda 1 in this total graph gonna be 6.803. Well, if you immunize A, you take this node out, you're gonna have a drop 0.0153. Well, if you do with A prime, not really much difference. Similar things for B. Can you see that? Similar things for B. Well, it's a huge difference for C, almost double, right? So, so we have to pick the C. Okay. All right. As I mentioned in the email, there were 3 questions. The first one is, how will the virus propagate? As we were talking about COVID-19, actually the answer is IS, because it won't give you a long-lasting immunity. So everybody will get infected again. And the second question in the email said, how long does it take to disinfect given infection rate and virus death rate? Well, we could expect a exponentially decay if below the threshold. Well, you can do anything else if it's above the threshold. The last one is, which is the best not to immunize if you have a limited budget? Well, the answer is gonna be you pick the one that's gonna have the maximal reduction, lambda 1A. Well, it's apparently you can't do anything to, beta and delta, because it's kind of like really hard to change it, but you could try it, like the universal virus infection rate and the virus, killing rate. But we could really deal with something with the lambda 1A, because the physical network you were interested in, and you can form an adjacency matrix and run the eigenvalues, and then help you to make the decisions. Okay? Either quarantine C or not. Okay. So that's pretty much of.
So I have another question then. I think you just finished. So I guess let's thank our speaker. And then I have so maybe other people have questions first, but I have a question also. So does anyone else have any questions before I start
have a question.
going off?
I have a question.
Okay.
So you compute largest eigenvalue for this adjacency matrix given a graph for a size of population. But what happens when the sample population is very large? The adjacency matrix is going to be very large, and computing this eigenvalue is going to be difficult. So are there any estimates for these largest eigenvalue for a very large adjacency matrix?
I haven't really done too much of the large, populations of the network. Well, you could always simplify it. I think it's called something like self-duplicated network. Well, like for example, maybe you are considering a community, but you could always consider this similar results gonna pose for the city. You understand?
So nodes are now cities or communities.
You could get the similar. Yeah,
Okay.
You could get a similar result from a small scale of the network. Well, you could extend to the large,
That's
network.
valid.
Yeah,
And I think
that's how they make the decision. Or you can simplify your largest, network.
So my question sort of builds on that a little bit. So to me, it doesn't seem as big of an issue. I can compute eigenvalues of large matrices. That's no problem. The question is how to pick what node to delete, because that you actually have to go through each node and pick out something. So what you just showed is essentially the answer is not immediately obvious. I mean, it was in that case, like you kind of saw that you had to pick out that node. But to me, the intuitive answer is still pick out remove the node with the highest degree, which isn't necessarily the case. But I guess, I mean, is there like a geometric characterization, I guess is what I want to ask, of what vertex reduces that eigenvalue by the most? I don't know if there's like a graph theory theorem about it.
For this case, I just calculate, but yeah, these are good questions. Yeah, is there any like tools we can directly use to show that which node gonna give us the maximum reductions? This graph I picked like a little bit tricky, right?
Yeah, it's like it's built so that it kind of does what you want, but it's a good counterexample, I think, because it goes against. I mean, it goes with intuition, but it also shows you how intuition can be like
right,
different in different cases, I guess. So it's
and maybe we could, yeah, maybe there's might be, but I did not know that if there's a tool that really give you a direct applications of how to pick the nodes give you. But that's a good question, you know. Or it's a good areas to explore, you know.
Yeah. Okay. So any other questions? I have like one or two more still, but any other questions from anyone else?
I do have a question. So, Alice, have you considered possibly seeing if this same sort of situation can be modeled, maybe using some martingale techniques? I mean, that's kind of my focus for this semester, I guess, and for these seminars is martingale techniques. So what I'm wondering is if perhaps you could somehow think of the number of infected as being maybe some kind of part of a martingale sequence, and then see if maybe game theoretical techniques could be applied.
Maybe, but I haven't. That might be you know, a good direction to go to. I haven't done that yet. Yeah, maybe.
Well,
It's
not
kind of
far
a-
already. It's already Markov chain, so
Yeah, so I mean, it sounds like it has the right stuff. Effectively, this would be like a two-player game where one player is maybe the population of people trying to cure, and then the other player is maybe the virus trying to infect. And so then you're trying to maximize outputs for one or the other.
It may be suitable for typical virus, you know. We were still on the, you know, on the process of understanding the COVID. So but I think in the history there might be some other type of communicable diseases that we can put for your theories into it, and then have some contributions to it, and we'll match the historical data, and also could predict some future you know, pandemic or whatever. That might be a very good you know, areas to explore.
Okay, that makes
But
sense.
I do not think that it's gonna be capable for COVID, because we were still, you know, because it's very large, it's worldwide. But there was some typical like virus only happening maybe in a country or in a city, and maybe isolated from the worldwide, and then we could only focus on the communications between not and, you know, between individuals. And yeah, maybe give you like what you just said, like two players and one, you know. Yeah, I do think that there might be some type of virus or
Okay,
other.
thank you.
Louis, you look like you got a
Sorry,
question.
I have another question. Yeah, just sort of basic actually. So what is the graph actually representing? It's representing transfer of populations between these nodes. Like physically, what's going on?
The nodes are the population, yeah. So they could be like population centers, or they could be individual people. I think.
You could be individual people. You could also consider like countries. You know, they have like, for example, there's a United States airports, maybe at Las Vegas or LA.
So that's sort of what I'm getting at, because shouldn't this be a sort of weighted graph? Because you can consider, like, if you're saying countries, like the now population entering
Well, the
and
weights are
leaving
given by the
North Korea
probability.
is very different from people entering and leaving, say, something like India or Europe.
It is weighted already. She has the probabilities weighting the edges, I think.
Oh, okay, I see. Okay.
So that was actually another question. I mean, I don't know how, but I remember. So this math club a couple weeks ago talked about something very close to this. It was like the same kind of idea, like modeling viruses on graphs or something. So the directed graph case, I assume, is completely different.
Right.
Do you know anything about this? I mean, because what would directed graph mean? I guess you can infect someone, but someone can't infect you. I guess.
Because if you were talking about COVID, maybe for others, or maybe for other like situations, but it's if you were talking about like infectious diseases, it's not always like directed. Like I give you, like you can't give it back.
Yeah,
to
it's
me.
kind of vice versa, I would say. So I never really got the directed, I guess, because this kid talked about this for a while, and I didn't really get the what it would mean. But maybe I mean, to me it seems like this is more realistic, anyways.
Mhm.
There was another question I had at the beginning. It was so we talked about their 0 being a fixed point, I guess. And I think it's baked into the model somewhere. But is it the only fixed point? Like, can there be other equilibrium solutions to this?
It's very easy to see. This is so I. You mean this one, right? This comes out because we want the probability goes to 0. So that's why I was just thinking that maybe 0 fit it.
The 0
and-
to subtraction fixed point.
Yeah, 0 is actually a fixed point, and then we have the following lemmas to show that. Well, it may have others. It depends on how you describe your system. It depends on the right hand side. Yeah.
How different is the time dependent version of this, or the not time dependent? How different is the continuous time version?
Because we were really consider the delta t very small, you know, very close to 0. Yeah, I think it's gonna hold for continuous.
It looks like it should be about the same, I would say, but I would have to play around with it. Will you send me these slides? These are it's kind of fun to think about.
I will share the slides.
Okay.
Okay. I also gave you some links I haven't clicked on, I think.
Yeah, I saw one at the beginning. There was one.
Here. Yeah, it's just from the Wikipedia. Yeah, and you can click on it, you can see. Actually, nowadays there were still papers published, you know, about those classical ones, you know, those classical models, and you can click on and get some update from it.
Okay, cool. So I think that's all the questions I had. Does anyone else have any other questions? If not, let's thank our speaker one more time. It was a fantastic talk. Thanks again, Alice, for talking. Let me stop the recording.
Thank you.